The universe is vast, mysterious, and seemingly infinite, stretching far beyond the comprehension of the human mind. But perhaps one of the greatest mysteries that grips scientists, astronomers, and cosmologists alike is not the size or age of the universe, but rather the enigma of what lies within it, specifically, a mysterious, invisible force that seems to be dictating its very expansion. This force, known as dark energy, is not only responsible for pushing the universe apart but also for doing so at an ever-accelerating rate. It defies everything we know about physics and gravity, and despite the vast advancements in technology and scientific understanding, dark energy remains one of the most elusive puzzles in the cosmos. But before we continue, if you like this type of videos, please subscribe to the channel and comment. Imagine the universe as a balloon. For much of human history, it was assumed that this balloon had been expanding at a relatively constant rate since the Big Bang. And for most of that time, it was believed that the gravitational pull of the universe's mass, its stars, planets, galaxies, would eventually slow down that expansion, perhaps even bringing it to a halt. But in the late 1990s, a stunning discovery shattered this long-held assumption. Instead of slowing down, the expansion of the universe was speeding up. It was as if some unseen hand was pushing the universe outward, making galaxies move away from each other faster than they ever had before. This force wasn't just unusual, it was baffling. Thus began the mystery of dark energy, a puzzle that has forced scientists to rethink everything they thought they knew about the universe's structure and fate. The discovery of dark energy was a direct result of studying distant supernovae, exploding stars whose brightness can be used as standard candles to measure the distance of objects in the universe. In 1998, two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, set out to measure the rate at which the universe was expanding. To their surprise, they found that these supernovae were dimmer, and therefore farther away, than expected. This implied that the universe was not only expanding, but its rate of expansion was accelerating. This was the exact opposite of what anyone expected. If gravity was the dominant force in the universe, then the mutual gravitational attraction between all matter should have been slowing the universe's expansion. But instead, something was acting against gravity, pushing space itself apart. This something was named dark energy, an entity that makes up approximately 68% of the total energy content of the universe. Since its discovery, dark energy has remained an enigma, a profound cosmic riddle. Its very nature challenges some of the most fundamental principles of physics, leaving scientists to grapple with questions about its origin, its behavior, and its ultimate role in the fate of the universe. Yet, despite the numerous questions, dark energy has become one of the most crucial elements in our understanding of cosmology. But what exactly is dark energy? Why does it exist, and how does it work? One of the first pieces of evidence for dark energy comes from observations of the cosmic microwave background, CMB, the afterglow of the Big Bang. By studying tiny fluctuations in the CMB, scientists have been able to deduce the overall shape and geometry of the universe. These observations suggest that the universe is flat, meaning it has a precise balance of matter and energy. However, the amount of matter, both regular and dark, accounts for only about 31.5% of the total energy content. This leaves a massive 68.5% unaccounted for, which cosmologists attribute to dark energy. But dark energy is not just a mysterious placeholder. It seems to have very real effects on the expansion of the universe. One of the leading theories to explain dark energy is the cosmological constant, a term first introduced by Albert Einstein in 1917 as part of his general theory of relativity. At the time, Einstein believed the universe was static, neither expanding nor contracting, and he introduced the cosmological constant to counteract the effects of gravity. After the discovery of the universe's expansion in the 1920s by Edwin Hubble, Einstein abandoned the cosmological constant, calling it his greatest blunder. However, with the discovery of dark energy, the cosmological constant has come back into play. According to this theory, dark energy is a form of energy that is inherent to space itself. As space expands, more of this energy is created, driving the acceleration of the universe's expansion. Unlike matter or radiation, the density of dark energy does not dilute as the universe grows larger. This means that dark energy remains constant over time, and as the universe expands, its influence becomes more and more dominant. This leads to a rather unsettling conclusion. If dark energy continues to drive the expansion of the universe, then galaxies, stars, and even planets will eventually drift farther and farther apart. Over billions and trillions of years, the universe could become a vast, cold, and lonely place, with galaxies so far apart that they would no longer be visible to one another. But while the cosmological constant is the simplest explanation for dark energy, it is by no means the only one. Some scientists have proposed that dark energy might be a dynamic field, something that changes over time and space. This idea, known as quintessence, suggests that dark energy could have been weaker in the past and could become stronger in the future, potentially leading to different outcomes for the universe's ultimate fate. Other theories suggest that dark energy could be a sign that our understanding of gravity is incomplete. According to this line of thinking, gravity might behave differently on cosmic scales than it does on smaller scales, such as within our solar system. In this scenario, dark energy wouldn't be a separate entity at all, but rather a manifestation of an unknown property of gravity itself. There are also those who speculate that dark energy might be connected to other, more exotic phenomena in physics. Some researchers have proposed that dark energy could be linked to the concept of extra dimensions, dimensions beyond the three spatial dimensions we experience in our everyday lives. In this view, dark energy might be a byproduct of how gravity and other forces behave in higher dimensions, something that we can't directly observe but which has a profound impact on the universe. The mystery of dark energy is further complicated by the fact that we don't fully understand how it interacts with the other components of the universe. For example, dark matter, another enigmatic substance that makes up about 27% of the universe, interacts with normal matter through gravity but does not emit light, making it invisible to our telescopes. Dark energy, on the other hand, doesn't appear to interact with matter in any direct way, aside from influencing the expansion of space. The relationship between dark matter and dark energy is still a topic of intense research, with some scientists speculating that the two might be connected in ways we don't yet understand. Ultimately, the true nature of dark energy remains one of the biggest unanswered questions in modern physics and cosmology. It challenges our understanding of the fundamental forces that govern the universe and raises profound questions about the future of the cosmos. Will the expansion of the universe continue to accelerate indefinitely, leading to a big freeze, where galaxies drift apart into isolation, or could dark energy reverse its behavior, leading to a big crunch, where the universe collapses in on itself? Some scientists even speculate that the effects of dark energy could fluctuate in such a way that the universe could experience a cycle of expansion and contraction, growing and shrinking over eons in a never-ending cosmic cycle. This idea, known as the oscillating universe theory, offers one possible way to reconcile the accelerating expansion with the possibility of a future contraction. As we look deeper into the cosmos, we are constantly gathering more data that helps us refine our understanding of dark energy. New experiments, such as those using powerful telescopes and satellites to measure the expansion rate of the universe, continue to shed light on this elusive force. However, every new piece of evidence seems to raise as many questions as it answers. The more we study dark energy, the more we realize just how little we truly understand it. One of the most important tools in this investigation is the study of large-scale cosmic structures, such as galaxy clusters and the cosmic web, the vast network of filaments composed of dark matter, galaxies, and gas that stretch across the universe. By observing how these structures have evolved over time, scientists can learn more about how dark energy affects the universe's expansion on a grand scale. One method used to measure the influence of dark energy is through something known as the baryon acoustic oscillations (BAO). BAO are periodic fluctuations in the density of the visible matter of the universe, which originated in the early universe when it was still a hot, dense plasma. These oscillations left an imprint on the distribution of galaxies, creating a sort of ripple pattern in the large-scale structure of the universe. By studying the distance between these ripples in different regions of space, astronomers can estimate how the universe has expanded over time. This, in turn, provides critical insights into the nature of dark energy and how it has influenced cosmic expansion throughout history. Another powerful technique for studying dark energy comes from gravitational lensing. This phenomenon occurs when light from distant galaxies is bent by the gravitational field of massive objects, such as galaxy clusters, creating a magnifying effect. Gravitational lensing allows astronomers to map the distribution of both visible matter and dark matter in the universe. By tracking how these objects and the space between them evolve over time, scientists can infer the influence of dark energy on the fabric of the cosmos. In addition to these observational techniques, theoretical physicists are hard at work developing new models to explain dark energy. One of the more speculative ideas is the multiverse theory, which suggests that our universe is just one of many, each with its own unique laws of physics and properties. In this scenario, dark energy might be a feature of our particular universe, but not necessarily a universal constant. This could mean that the amount and nature of dark energy might vary across different universes, offering one possible explanation for why its properties seem so strange and difficult to reconcile with our current understanding of physics. Some researchers have even proposed that dark energy might not exist at all, at least, not in the way we currently think of it. Instead, they suggest that the accelerated expansion of the universe could be explained by modifications to Einstein's theory of general relativity. These modified gravity theories propose that gravity behaves differently on the largest scales of the universe than it does in more localized regions, such as within galaxies or solar systems. If this is the case, dark energy might simply be an illusion, a byproduct of our incomplete understanding of how gravity works on cosmological scales. One intriguing possibility is that dark energy could be related to the concept of vacuum energy, which arises from the strange and counterintuitive nature of quantum mechanics. According to quantum theory, even the vacuum of space, what we think of as empty space, is not truly empty. Instead, it is filled with virtual particles that constantly pop in and out of existence. These virtual particles generate a small amount of energy, which could contribute to the expansion of the universe. However, attempts to calculate the exact amount of vacuum energy predicted by quantum mechanics have yielded results that are wildly off from the observed value of dark energy, leading to what physicists refer to as the cosmological constant problem. Despite the many theories and models proposed to explain dark energy, the truth is that we are still far from a definitive answer. The field of cosmology is filled with uncertainties, and dark energy remains at the center of some of the most profound and challenging questions in modern science. As new telescopes and observatories come online, such as the James Webb Space Telescope and the upcoming Euclid mission, we may be on the cusp of gaining new insights into the nature of dark energy and its role in shaping the universe. The implications of dark energy extend far beyond the realm of theoretical physics. Understanding the nature of dark energy could have profound implications for our understanding of the ultimate fate of the universe. If dark energy continues to drive the acceleration of the universe's expansion, then the long-term future of the cosmos looks bleak. Over time, galaxies will drift farther and farther apart, becoming isolated from one another as the space between them expands. Stars will burn out, black holes will evaporate, and eventually, the universe will become a cold, dark, and empty place, a scenario known as the Big Freeze. On the other hand, if dark energy were to change its behavior, it could lead to dramatically different outcomes. For example, if dark energy were to weaken or reverse, it could cause the universe's expansion to slow down and eventually halt. This could lead to a scenario in which the universe begins to contract, ultimately collapsing in on itself in a big crunch. In this case, the universe would end not in freezing isolation, but in a fiery cataclysm as all matter and energy are crushed together in a final singularity. There is also the possibility of an even stranger fate, known as the Big Rip. In this scenario, dark energy's influence would continue to grow stronger over time, causing the expansion of the universe to accelerate to an extreme degree. Eventually, the expansion would become so rapid that it would overcome even the forces that hold galaxies, stars, planets, and even atoms together. In the final moments before the Big Rip, space itself would tear apart, resulting in the disintegration of all matter in the universe. While these scenarios may sound like the stuff of science fiction, they are based on real scientific models and observations. The nature of dark energy is deeply connected to the fate of the universe, and by studying it, we are not only learning more about the forces that govern the cosmos but also glimpsing the possible futures that lie ahead. In many ways, the mystery of dark energy is a humbling reminder of how much we have yet to discover about the universe. Despite centuries of scientific progress, we are still grappling with some of the most fundamental questions about the nature of reality. What is dark energy? Why does it exist? And what role does it play in the grand scheme of the cosmos? These questions are not just academic, they touch on the very essence of our existence and the future of everything we know. As we continue to explore the universe, we may one day unlock the secrets of dark energy and gain a deeper understanding of the forces that shape our reality. But for now, dark energy remains one of the most tantalizing and perplexing mysteries of the cosmos, a force that drives the expansion of space itself, yet eludes our grasp. It is a reminder that the universe is far more complex and wondrous than we can possibly imagine, and that every answer we uncover leads to new and deeper questions. The search for answers about dark energy is part of a broader quest to understand the universe's most fundamental forces and laws. While we have made remarkable strides in understanding the cosmos, unraveling the mysteries of gravity, electromagnetism, and the strong and weak nuclear forces, dark energy stands apart as something truly mysterious. This elusive force is believed to account for about 68% of the universe's total energy content, making it the dominant component of the cosmos. Yet, we have no direct means of detecting it or understanding its true nature. In fact, its discovery was a shock to the scientific community. The journey to uncover the existence of dark energy began in the late 20th century when two independent teams of astronomers set out to measure the rate of the universe's expansion. These teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, were studying distant supernovae, specifically Type I supernovae, which are exploding stars that can serve as standard candles for measuring cosmic distances. By observing these supernovae in distant galaxies, the astronomers hoped to determine whether the universe's expansion was slowing down due to the gravitational pull of matter, as most cosmologists expected at the time. To their astonishment, the data revealed that the opposite was happening. The expansion of the universe was not slowing down, but accelerating. This was a groundbreaking discovery, suggesting that some unknown force, dubbed dark energy, was pushing the universe apart at an ever-increasing rate. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for their discovery, which fundamentally altered our understanding of the cosmos. Since this discovery, the study of dark energy has become one of the most active areas of research in cosmology. Yet, despite decades of effort, we are still left with more questions than answers. One of the most puzzling aspects of dark energy is its apparent uniformity. Unlike dark matter, which clumps together to form galaxies and other structures, dark energy appears to be evenly distributed throughout space. This uniform distribution makes it incredibly difficult to detect or measure directly, as it exerts no localized gravitational effects that we can observe. One of the key pieces of evidence supporting the existence of dark energy comes from observations of the cosmic microwave background (CMB), the faint afterglow of the Big Bang that fills the universe. The CMB provides a snapshot of the universe as it existed roughly 380,000 years after the Big Bang, when the first atoms were forming, and light was able to travel freely through space. By studying the tiny fluctuations in the CMB, astronomers can infer important details about the universe's composition, including the presence of dark energy. These observations reveal that the universe is not only filled with ordinary matter, the atoms that make up stars, planets, and galaxies, but also with dark matter, which interacts with regular matter through gravity, and dark energy, which exerts a repulsive force driving the accelerated expansion. The precise nature of dark energy, however, remains a profound mystery. While it is often described as a negative pressure that counteracts the attractive force of gravity, This is a simplistic characterization that does not fully capture the complexity of the phenomenon. Several theories have been proposed to explain the nature of dark energy, but none have been conclusively proven. One of the simplest and most widely accepted explanations is the cosmological constant, a term originally introduced by Albert Einstein in his equations for general relativity. When Einstein first formulated his theory of general relativity in 1915, he was confronted with the problem that his equations predicted a dynamic universe, either expanding or contracting, whereas the prevailing view at the time was that the universe was static and unchanging. To reconcile his theory with this belief, Einstein introduced the cosmological constant, a term that acted as a repulsive force to counterbalance the attractive force of gravity and maintain a static universe. However, when Edwin Hubble discovered in 1929 that the universe was, in fact, expanding, Einstein abandoned the cosmological constant, calling it his biggest blunder. Ironically, the concept of a cosmological constant has since been revived to explain the effects of dark energy. In modern cosmology, the cosmological constant is interpreted as a form of vacuum energy, a property of empty space itself that causes the universe to expand at an accelerating rate. While the cosmological constant provides a convenient explanation for dark energy, it raises significant theoretical challenges. One of the most perplexing issues is the fine-tuning problem. The observed value of dark energy is extremely small compared to the predictions of quantum field theory, which suggests that the vacuum energy should be much larger, by as much as 120 orders of magnitude. This discrepancy has led many physicists to suspect that the cosmological constant is not the whole story and that some deeper explanation is needed. In response to these challenges, alternative theories of dark energy have been proposed. One popular idea is that dark energy might be a dynamic field, similar to the scalar fields used in particle physics. In this scenario, dark energy could be driven by a hypothetical field known as quintessence. Unlike the cosmological constant, which is a fixed value, quintessence would evolve over time, potentially explaining why the universe's expansion is accelerating now but may have behaved differently in the past. Another intriguing possibility is that dark energy could be linked to extra dimensions beyond the three spatial dimensions and one-time dimension we experience. Some theories in string theory, for example, propose that the universe has additional hidden dimensions that could influence the behavior of dark energy. These extra dimensions might help explain why dark energy seems so weak compared to other forces, as its effects could be diluted across these additional dimensions. Despite the many theories, the true nature of dark energy remains elusive, and it is possible that the answer lies in entirely new physics that we have yet to discover. One thing is certain: the discovery of dark energy has opened up a vast and largely unexplored frontier in cosmology, challenging our understanding of the universe at the most fundamental level. The stakes of understanding dark energy are incredibly high, not just for cosmology but for the future of the universe itself. As mentioned earlier, the fate of the cosmos depends on the nature of dark energy. If dark energy remains constant, as predicted by the cosmological constant model, the universe will continue to expand at an accelerating rate, leading to a cold, dark future where galaxies drift apart and stars fade into darkness. However, if dark energy changes over time, the universe could face a very different fate. If dark energy weakens or reverses, the expansion of the universe could slow down, eventually leading to a contraction that culminates in a big crunch. Alternatively, if dark energy grows stronger, it could lead to the catastrophic Big Rip, in which the fabric of space itself is torn apart. The potential scenarios for the universe's ultimate fate all hinge on dark energy's future behavior, and each outcome is as dramatic as it is mysterious. The Big Rip scenario is perhaps the most terrifying of these possibilities. In this case, dark energy's repulsive force would continue to grow stronger over time, eventually overpowering all other forces in the universe. As this force increases, it would first rip apart galaxy clusters, then individual galaxies, and finally, even the atoms and subatomic particles that make up matter itself. In the final moments of the universe, everything, down to the most fundamental components of reality, would be torn apart, leaving nothing but a cold and empty void. The Big Crunch, on the other hand, represents the opposite extreme. In this scenario, dark energy would weaken or reverse, allowing gravity to gain the upper hand. The expansion of the universe would gradually slow down and eventually stop, followed by a period of contraction. Over billions of years, galaxies would begin to draw closer together, and temperatures would rise as the universe became increasingly dense. If this process continues unchecked, the universe could collapse into a singularity, a point of infinite density, similar to the one that preceded the Big Bang. Some theorists even speculate that this collapse could trigger a new Big Bang, leading to a cyclical model of the universe, where periods of expansion and contraction alternate in an eternal cycle. A third, somewhat more optimistic possibility is the Big Freeze, or heat death, scenario. If dark energy remains constant, as predicted by the cosmological constant model, the universe will continue to expand forever, but at an ever-accelerating rate. Over time, galaxies will drift farther and farther apart, and the stars within them will burn out, leaving behind cold remnants like white dwarfs, neutron stars, and black holes. Eventually, even black holes will evaporate through a process known as Hawking radiation, leaving behind a cold, dark, and empty universe. In this scenario, the universe doesn't end with a violent collapse or catastrophic rip, but with a slow fading into darkness, where all activity ceases and the cosmos reaches a state of maximum entropy, an ultimate thermodynamic equilibrium. While each of these potential outcomes is starkly different, they all depend on the fundamental properties of dark energy, which we still do not fully understand. The quest to unlock the mysteries of dark energy is not just about answering abstract questions about the universe's expansion, it is about determining the ultimate fate of everything that exists. The challenge of studying dark energy lies in its elusive nature. Unlike ordinary matter, which interacts through electromagnetic forces and can be observed through light, or dark matter, which interacts gravitationally, dark energy does not seem to interact in any detectable way other than through its influence on the expansion of the universe. This makes it incredibly difficult to study directly. Most of what we know about dark energy comes from indirect evidence, primarily through observations of large-scale cosmic structures and the universe's overall geometry. One of the key tools for studying dark energy is the large-scale distribution of galaxies in the universe. By mapping the positions of millions of galaxies across vast distances, astronomers can trace the growth of cosmic structures over time. These observations provide crucial insights into how the universe has expanded under the influence of dark energy. For example, galaxy surveys have revealed that the universe's expansion began accelerating about 5 billion years ago, roughly halfway through its current age. This discovery suggests that dark energy has only recently come to dominate the universe's dynamics, after a long period in which gravity was the dominant force shaping cosmic evolution. Another important method for studying dark energy involves measurements of the cosmic microwave background, CMB, radiation. The CMB is a relic of the early universe, providing a snapshot of conditions as they existed just 380,000 years after the Big Bang. By analyzing the tiny fluctuations in the CMB's temperature and polarization, cosmologists can infer important details about the universe's composition, including the presence of dark energy. The precise measurements of the CMB made by missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided some of the strongest evidence for the existence of dark energy, helping to refine our understanding of its role in the universe. In addition to these observational techniques, theoretical physicists have been working to develop models that might explain the nature of dark energy. One of the most popular theoretical frameworks for understanding dark energy is quantum field theory, QFT, which describes the universe in terms of fields that permeate space and time. In QFT, particles are seen as excitations of underlying fields. One of these fields is the vacuum energy, a form of energy that is thought to exist even in empty space. In this context, dark energy could be understood as a form of vacuum energy, which exerts a negative pressure that drives the accelerated expansion of the universe. However, as mentioned earlier, this explanation raises significant problems, particularly the so-called Cosmological constant problem. According to quantum field theory, the vacuum energy should be extraordinarily large, many orders of magnitude larger than the observed value of dark energy. This enormous discrepancy has led some physicists to suspect that our current understanding of quantum field theory may be incomplete, and that some new physics may be needed to explain dark energy. Other proposed explanations for dark energy involve modifications to general relativity, the theory of gravity formulated by Einstein in the early 20th century. While general relativity has been extraordinarily successful in describing the behavior of gravity on both small and large scales, it may not be the final word on how gravity works. Some theorists have suggested that dark energy could be a manifestation of a more complex gravitational theory that goes beyond Einstein's equations. For example, one idea is that dark energy could be linked to extra dimensions, hidden dimensions that are not directly observable but could influence the behavior of gravity on large scales. These alternative theories of gravity offer intriguing possibilities for understanding dark energy, but they are still highly speculative, and much more work is needed to determine whether they can explain the observed behavior of the universe. In the meantime, cosmologists continue to gather data from a wide range of observations, hoping to uncover new clues about the nature of dark energy. Despite the enormous challenges involved in studying dark energy, there is hope that we may eventually solve this profound mystery. Several upcoming missions and observatories are poised to revolutionize our understanding of dark energy and the universe's expansion. One of the most eagerly anticipated projects is the European Space Agency's Euclid mission, which is scheduled to launch in the near future. Euclid will survey billions of galaxies across vast cosmic distances, providing the most detailed map yet of the large-scale structure of the universe. By studying how galaxies are distributed and how they have evolved over time, Euclid aims to shed light on the behavior of dark energy and its role in shaping the cosmos. Another major project is the Rubin Observatory's Legacy Survey of Space and Time, LSST, which will conduct a 10-year survey of the southern sky, capturing images of billions of galaxies and measuring their distances and motions. The data collected by LSST will be invaluable for understanding how dark energy has influenced the expansion of the universe and how it might evolve in the future. These upcoming projects, like the Euclid mission and the Rubin Observatory's LSST, will add an unprecedented amount of precision to our understanding of dark energy. They will be able to map the large-scale structure of the universe in exquisite detail, providing fresh insights into how galaxies have moved and evolved under the influence of dark energy. The hope is that this wealth of new data will finally allow us to discern whether dark energy is truly constant, as the cosmological constant model suggests, or whether its properties evolve over time, as some dynamic dark energy models propose. One dynamic model of dark energy that has garnered attention is the idea of quintessence. Unlike the cosmological constant, which assumes dark energy is static, quintessence suggests that dark energy is a field that changes over time, much like how fields in particle physics evolve. This evolving energy field could explain why dark energy's influence became dominant only relatively recently in cosmic history. If quintessence is correct, then dark energy might weaken or even reverse in the distant future, potentially leading to a scenario like the Big Crunch, where the universe's expansion slows and eventually collapses. The challenge with quintessence and other dynamic dark energy theories is that they require new physics beyond what we currently understand. Theories like these need to explain why dark energy would have such a peculiar behavior, ramping up just as the universe reaches a certain age, without invoking finely tuned coincidences. Nevertheless, the quintessence hypothesis remains one of the most actively explored alternatives to the cosmological constant. In addition to theoretical advances, observational breakthroughs could come from even more futuristic missions, such as the proposed NASA mission known as the Wide Field Infrared Survey Telescope, WFIRST, now renamed the Nancy Grace Roman Space Telescope. This spacecraft is designed to map the distribution of dark matter and dark energy across the universe with unprecedented precision. It will use a technique called weak gravitational lensing, where light from distant galaxies is subtly bent by massive objects like galaxy clusters as it travels to Earth. By observing these distortions, scientists can infer the distribution of both dark matter and dark energy, further refining our understanding of how these components shape the universe. Gravitational waves, ripples in space-time caused by the movement of massive objects, might also play a role in solving the mystery of dark energy. The detection of gravitational waves from colliding black holes and neutron stars has already revolutionized our understanding of the universe, and some scientists believe that further gravitational wave observations could reveal more about dark energy's nature. Specifically, by studying how gravitational waves propagate across the expanding universe, it may be possible to determine whether dark energy is truly a constant force or if its strength varies over time. As cosmologists continue to probe the universe with increasingly sophisticated instruments, one thing remains clear: the mystery of dark energy is one of the deepest and most profound questions in science today. It touches on the very nature of space, time, and existence itself. The discovery of dark energy has already revolutionized our understanding of the cosmos, forcing us to rethink fundamental concepts of physics, but the full story remains elusive. Whether dark energy turns out to be a simple cosmological constant or a more complex, dynamic force, solving this mystery will almost certainly require new physics and possibly a new understanding of the universe's most fundamental forces. Beyond its role in driving the expansion of the universe, dark energy could also be linked to other unexplained phenomena in cosmology and particle physics. Some theorists have speculated that dark energy might be related to the mysterious missing pieces in the standard model of particle physics. For example, some models suggest that dark energy could be connected to hypothetical particles like axions, extremely light particles that could also be candidates for dark matter. If true, this would represent a profound unification of two of the universe's greatest mysteries, dark energy and dark matter. Other speculative ideas include the possibility that dark energy is a sign of extra dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. String theory, one of the leading candidates for a theory of everything, predicts the existence of additional hidden dimensions that could influence how gravity behaves on large scales. Some versions of string theory suggest that the accelerated expansion of the universe could be a consequence of how gravity leaks into these extra dimensions. While these ideas are still highly speculative and far from being confirmed, they demonstrate the range of possibilities that scientists are considering in their quest to understand dark energy. However, even as we explore these wild possibilities, we must remain grounded in the hard observational evidence. The next generation of cosmological surveys will be critical in distinguishing between different theories of dark energy and helping to resolve this cosmic mystery. By continuing to observe the universe in greater detail and refining our models, we can hope to gradually peel back the layers of the dark energy enigma. At its core, the mystery of dark energy forces us to confront some of the most fundamental questions about the nature of the cosmos. What is the true nature of space and time? How do the forces of the universe interact with one another? And perhaps most importantly, what does the future hold for the universe as a whole? The implications of dark energy extend far beyond the realm of cosmology. If dark energy is found to be linked to new physics, it could lead to a revolution in our understanding of the laws of nature, much like how Einstein's theory of general relativity transformed our view of gravity. The discovery of dark energy has already upended the 20th century view of the universe, which assumed that gravity would eventually slow down the universe's expansion. Instead, we now know that the universe is not only expanding but accelerating, a discovery that has forced us to rethink everything we thought we knew about cosmic evolution. Perhaps even more profoundly, dark energy challenges our intuitions about the fate of the cosmos. The idea that the universe might expand forever, with galaxies growing ever more distant from one another until they vanish from sight, is deeply unsettling. It suggests a future where the universe becomes a cold, empty void, devoid of stars, galaxies, and even atoms. Yet, paradoxically, the fact that we are alive today, in a universe where galaxies and stars still exist, could be viewed as a stroke of cosmic luck. We are living in what may be a brief window of cosmic history, where the universe is still rich in structure and activity, but where dark energy's grip is slowly tightening. As we peer into the deep future of the universe, we are forced to confront the idea that all of the wonders of the cosmos, the galaxies, stars, and planets that populate the night sky, may eventually fade into oblivion. But at the same time, the mystery of dark energy reminds us that the universe is full of surprises, and that our understanding of its deepest workings is still in its infancy. As we continue to probe the cosmos, who knows what other mysteries we will uncover? The quest to understand dark energy is not just about solving an abstract puzzle. It is about coming to terms with our place in a universe that is far more mysterious and complex than we ever imagined. Whether we ultimately discover that dark energy is a constant force or a dynamic field, the search for answers will undoubtedly lead to new discoveries that will transform our understanding of the cosmos. In the end, the mystery of dark energy may be one of the keys to unlocking the deepest secrets of the universe. One of the most captivating aspects of the dark energy mystery is its profound implications for the ultimate fate of the universe. The future of the cosmos, in many ways, hinges on the nature of dark energy. Since dark energy drives the expansion of the universe, understanding its properties is essential to predicting how the universe will evolve on the grandest of scales. If dark energy truly is a cosmological constant, then the universe will continue to expand at an accelerating rate indefinitely. Galaxies, which are currently bound together in clusters, will drift farther and farther apart. Over billions of years, the night sky will grow emptier as distant galaxies recede beyond the observable horizon, moving away faster than the speed of light due to the expansion of space itself. The stars within galaxies will eventually exhaust their fuel, becoming cold remnants like white dwarfs and neutron stars. The end result is often referred to as the Big Freeze, or heat death. In this scenario, the universe approaches a state of maximum entropy, where all thermodynamic processes cease, and the universe becomes a cold, dark, and empty place. Matter will be so spread out that new stars will no longer form, and even black holes will eventually evaporate due to Hawking radiation, leaving behind nothing but diffuse particles in an ever-expanding void. This grim outcome is one of the most widely accepted possibilities based on current observations of dark energy. Yet, the universe's fate is far from settled, as alternative models of dark energy present different possibilities. For instance, if dark energy's properties were to change over time, the cosmic future could take a dramatically different course. One such alternative is the notion of a Big Rip. In this scenario, dark energy becomes progressively stronger over time, increasing its repulsive force to the point where it overcomes all other forces, including gravity, electromagnetic forces, and even the strong nuclear force. In the far future, as dark energy grows in strength, it could tear galaxies apart, then rip apart stars, planets, and eventually atoms themselves. The Big Rip scenario envisions a universe that ends in a violent, catastrophic disintegration of all matter, with space itself being torn apart. The timing of this event, if it were to happen, would depend on the exact nature of dark energy, but some calculations suggest that the Big Rip could occur tens of billions of years from now. Other models introduce the possibility of the opposite outcome, a Big Crunch. This would occur if dark energy were not constant but instead reversed its behavior, changing from a repulsive force to an attractive one. In this scenario, after a period of accelerated expansion, the universe would stop expanding and begin to contract. Galaxies would start moving back toward one another, and the universe would collapse in on itself, culminating in a singularity similar to the Big Bang, but in reverse. The universe could end in a fiery, high-density state, essentially resetting the cosmic clock. This idea raises tantalizing questions about the possibility of a cyclic universe, where each Big Crunch leads to a new Big Bang, perpetuating an eternal cycle of cosmic birth and death. A less extreme variant of this idea is known as the Big Bounce, which suggests that instead of ending in a singularity, the universe could rebound from its contraction phase into another expansion, essentially creating a series of bounces. Each bounce would lead to a new period of cosmic expansion, potentially giving rise to different physical conditions and laws in each cycle. Although speculative, these models offer intriguing alternatives to the notion of an eternally expanding universe. Another model that has gained some traction is the idea of phantom energy. This hypothetical form of dark energy would have properties that violate certain energy conditions in general relativity. Phantom energy would be even more repulsive than the form of dark energy predicted by the cosmological constant, leading to a more dramatic acceleration of the universe's expansion. Over time, phantom energy could cause galaxies to recede from each other at an accelerating pace, leading to a scenario similar to the Big Rip, but occurring even more rapidly. Although no observational evidence currently supports the existence of phantom energy, it remains a possibility within the framework of theoretical physics. These potential fates of the universe illustrate just how central dark energy is to our understanding of the cosmos. The nature of dark energy not only determines the large-scale structure and evolution of the universe but also holds the key to its ultimate destiny. Yet, despite its critical importance, dark energy remains one of the most enigmatic forces in physics. In addition to the various cosmological models, some researchers are exploring the possibility that dark energy might not exist at all, or at least not in the way we currently understand it. Instead of dark energy being a fundamental force, it could be a consequence of the way we understand gravity. One alternative theory that challenges the need for dark energy is modified gravity. In these models, the laws of gravity might behave differently on cosmic scales compared to how they work within our solar system. One such theory is known as F.R. gravity, where the force of gravity is modified by introducing additional terms to Einstein's field equations. These modifications could mimic the effects of dark energy by causing the universe to accelerate without invoking a mysterious, unseen force. Another approach involves theories like brane-world cosmology, inspired by string theory, where our universe is viewed as a brane, embedded in a higher dimensional space. In these models, the accelerated expansion of the universe could be explained by interactions with these extra dimensions, bypassing the need for dark energy altogether. However, testing these modified gravity theories is extremely difficult. While they offer an alternative explanation for cosmic acceleration, they must also account for the precise observations that have already been made, such as the cosmic microwave background and large-scale galaxy distribution. So far, dark energy remains the simplest and most widely accepted explanation, but alternative ideas remain under investigation, as they offer potential insights that could revolutionize our understanding of both gravity and the universe. In the search for answers, one of the biggest questions that remains is whether dark energy interacts with other forces and particles in the universe. For example, could dark energy be linked to the mysterious dark matter that makes up roughly 27% of the universe's mass energy content? While dark energy and dark matter appear to behave very differently, dark matter exerts a gravitational pull, while dark energy drives the universe's expansion. They may still be connected in ways we have yet to discover. One theory that attempts to link dark energy and dark matter is known as the dark sector. In this model, dark energy and dark matter are both part of a hidden sector of the universe that interacts with ordinary matter only through gravity. The dark sector could contain a variety of exotic particles and forces that we have yet to detect. If these forces exist, they might provide a deeper understanding of how dark energy and dark matter influence each other and shape the universe. Furthermore, some physicists have suggested that dark energy could be a remnant of an earlier phase of the universe's evolution. During the inflationary period, shortly after the Big Bang, the universe underwent a brief but extremely rapid expansion. Some theories suggest that dark energy could be the leftover energy from this inflationary phase, which is now driving the current acceleration of the universe. If this is the case, then dark energy might not be a fundamental aspect of the universe but rather a transient phenomenon that will eventually decay or change over time. As we continue to probe the mysteries of dark energy, it becomes clear that solving this puzzle will require a combination of observational breakthroughs, theoretical innovations, and perhaps even a rethinking of our most basic assumptions about the nature of the universe. Whether dark energy is a cosmological constant, a dynamic field, or a consequence of modified gravity, its discovery has already reshaped our understanding of the cosmos in profound ways. The journey to unravel its true nature is one of the most exciting frontiers in modern science. The mystery of dark energy has not only reshaped our understanding of the cosmos but also forced us to confront some of the deepest questions in physics, cosmology, and philosophy. Its very existence challenges the way we think about the forces that govern the universe and raises profound questions about the nature of reality itself. While we currently observe dark energy's effects on the large-scale structure of the universe, understanding what it is and where it comes from requires a level of insight that may revolutionize physics in ways comparable to the discoveries of relativity or quantum mechanics. At its core, dark energy is a problem that exists at the intersection of quantum mechanics and general relativity, two of the most successful but still fundamentally incompatible theories in physics. Quantum mechanics governs the behavior of particles on the smallest scales, while general relativity describes gravity and the structure of spacetime on cosmic scales. Yet, when applied to the problem of dark energy, these two theories yield vastly different predictions, leading to what is known as the cosmological constant problem. Quantum field theory, which describes the behavior of particles and forces on the quantum level, predicts that empty space should be teeming with energy due to the constant fluctuations of quantum fields. However, the amount of energy predicted by quantum field theory is vastly larger than what we observe as dark energy. In fact, the difference between the two predictions is often described as one of the largest discrepancies in physics, a staggering 120 orders of magnitude. This mismatch suggests that something fundamental is missing from our understanding of the connection between quantum mechanics and gravity. Resolving this discrepancy could point the way toward a unified theory of quantum gravity, one of the ultimate goals of modern physics. String theory, one of the leading candidates for a theory of quantum gravity, offers some tantalizing possibilities for explaining dark energy. In string theory, the fundamental building blocks of the universe are not point-like particles but rather tiny, vibrating strings. These strings exist in a higher dimensional space, and their vibrations give rise to the particles and forces we observe. One of the most intriguing aspects of string theory is that it naturally predicts the existence of a large number of possible universes, what is often referred to as the multiverse. In the context of string theory, dark energy might be a consequence of the particular vacuum state that our universe happens to occupy within the multiverse. Each vacuum state corresponds to a different configuration of the extra dimensions predicted by string theory, and different configurations would lead to different values of the cosmological constant, or dark energy. Our universe might be one of many in the multiverse, each with its own value for dark energy, and we just happen to live in a universe where dark energy is small enough to allow galaxies, stars, and life to form. This idea, while speculative, suggests that the value of dark energy in our universe could be explained through a kind of cosmic selection effect, known as the anthropic principle. According to this principle, the reason we observe a particular value for dark energy is that it is the only value that allows for the existence of observers like us. In universes with too much dark energy, the accelerated expansion would prevent galaxies from forming, while in universes with too little dark energy, the universe might have collapsed before life could emerge. This anthropic reasoning is controversial, as it implies that the properties of our universe are, in some sense, an accident of cosmic history rather than the result of deeper physical principles. While the multiverse and anthropic explanations for dark energy are intriguing, they also highlight the limitations of current scientific knowledge. Testing these ideas is extremely challenging, as we have no way of directly observing other universes or probing the higher dimensional space predicted by string theory. However, advances in observational cosmology, such as more precise measurements of the cosmic microwave background and large-scale structure, could provide indirect evidence for or against these theories in the future. Beyond string theory, there are other theoretical frameworks that attempt to explain the origin and nature of dark energy. One possibility is that dark energy could be a form of vacuum energy associated with quantum fluctuations in empty space. In this view, dark energy is not a new kind of force or field but rather a property of spacetime itself. This idea, rooted in quantum field theory, suggests that dark energy is an intrinsic feature of the vacuum, and its effects become noticeable only on the largest scales. However, as mentioned earlier, the predicted value of vacuum energy in quantum field theory is vastly larger than what we observe, so significant theoretical work is needed to reconcile this idea with the observed acceleration of the universe. Another intriguing possibility is that dark energy could be a manifestation of a more fundamental symmetry of nature. In particle physics, symmetries play a crucial role in determining the behavior of particles and forces. Some researchers have suggested that dark energy might be linked to a previously undiscovered symmetry that operates on cosmic scales. For example, it could be related to supersymmetry, a theoretical symmetry that predicts the existence of partner particles for all known particles. Supersymmetry has not yet been observed in experiments, but if it exists, it could provide a natural explanation for the small value of dark energy. Other approaches consider dark energy as a dynamic field that evolves over time, rather than a constant. These models, known as quintessence theories, propose that dark energy is associated with a slowly evolving scalar field that changes its strength as the universe expands. Unlike the cosmological constant, which remains constant throughout cosmic history, quintessence allows for the possibility that dark energy's influence could change over time. In some models, the field driving dark energy could become weaker or stronger in the future, leading to different cosmic outcomes. For example, if the field decays over time, the universe might eventually stop accelerating and settle into a more stable state. Alternatively, if the field strengthens, it could lead to a Big Rip scenario, where the universe is torn apart. Quintessence models are attractive because they provide a more flexible framework for understanding dark energy and its role in the evolution of the universe. However, they also introduce new challenges, such as the need to explain why the field driving dark energy has the particular properties it does and how it interacts with other forces and particles. Additionally, testing these models requires precise measurements of the expansion rate of the universe over time, which will be a major focus of future observational efforts. One of the most promising tools for studying dark energy is the next generation of large-scale astronomical surveys, which will map the distribution of galaxies and matter across the universe with unprecedented precision. These surveys, such as the Dark Energy Survey and the upcoming Euclid mission, aim to measure the expansion history of the universe by observing the redshifts of distant galaxies and the large-scale structure of the cosmos. By comparing these observations with theoretical models, astronomers hope to constrain the properties of dark energy and determine whether it is truly a cosmological constant, a dynamic field, or something else entirely. In addition to large-scale surveys, other experiments are focused on studying the cosmic microwave background (CMB), the faint afterglow of the Big Bang that permeates the universe. The CMB provides a snapshot of the universe as it was just 380,000 years after the Big Bang, and its detailed structure contains valuable information about the universe's expansion history and the role of dark energy. Future CMB experiments, such as the Simons Observatory and the CMB-S4 project, will provide even more precise measurements of the CMB, helping to refine our understanding of dark energy and its effects on the early universe. While these observational efforts are likely to yield new insights into dark energy, they may also raise new questions. The nature of dark energy is so deeply intertwined with the fundamental structure of the universe that any breakthrough in understanding it could have profound implications for our broader understanding of physics. Solving the dark energy puzzle may require revisiting some of the most basic assumptions about the nature of space, time, and matter. In this sense, dark energy represents not only a challenge but also an opportunity to push the boundaries of scientific knowledge and discover new laws of nature. As we continue to explore the cosmos and unravel its mysteries, dark energy remains one of the most tantalizing enigmas on the horizon. Whether it is a new force of nature, a property of the vacuum, or a sign of deeper symmetries or dimensions, its discovery has already revolutionized our understanding of the universe. Yet, as with many great scientific mysteries, the more we learn about dark energy, the more questions arise. The ultimate nature of dark energy may remain hidden for years or even decades to come, but the search for answers is sure to lead to new discoveries that will reshape our view of the cosmos and our place within it. The search for answers about dark energy is likely to be a long and difficult journey. Yet, as history has shown, some of the greatest breakthroughs in science have come from confronting the most perplexing and seemingly insurmountable problems. Much like the discovery of quantum mechanics in the early 20th century or the revelation of general relativity, solving the dark energy mystery could open the door to a new era of scientific understanding. One of the fascinating aspects of the dark energy puzzle is its potential to bridge some of the deepest chasms in physics. The fundamental incompatibility between quantum mechanics and general relativity has long been one of the greatest challenges in theoretical physics. Dark energy sits at the crossroads of these two theories, as it involves both the large-scale structure of the universe and the behavior of quantum fields. If we can figure out what dark energy truly is, we may finally discover a way to unite these two pillars of modern physics into a single coherent framework, leading us closer to the ultimate goal of a theory of everything. But what if dark energy is something even more exotic than we imagine? Could it point to entirely new dimensions of reality or undiscovered forces? Some scientists have suggested that dark energy could be a window into extra dimensions beyond the familiar three of space and one of time. In these higher dimensions, space and time might behave in ways that are fundamentally different from what we experience in our everyday lives. Dark energy could be the key to unlocking these extra dimensions and understanding how they shape the universe on both large and small scales. These higher dimensions are not just speculative musings of theoretical physicists. They arise naturally in certain models of string theory and other approaches to quantum gravity. If dark energy is indeed related to higher dimensions, it could help explain why gravity is so much weaker than the other fundamental forces. The idea is that gravity might leak into these extra dimensions, making it appear weaker in our familiar four-dimensional spacetime. Dark energy could be a manifestation of this hidden gravitational force, interacting with the fabric of spacetime in ways that we are only beginning to grasp. If higher dimensions are real, they could also provide a new perspective on the fate of the universe. One of the most intriguing possibilities is that dark energy might eventually cause the universe to roll into a new vacuum state, in which the laws of physics are different from those we currently experience. This scenario is sometimes referred to as vacuum decay, and it would involve a catastrophic change in the nature of the universe itself. In this new vacuum, particles might behave differently, the constants of nature might take on new values, and life as we know it could become impossible. While this may sound like science fiction, vacuum decay is a real possibility in certain theoretical models, particularly those involving quantum fields and higher dimensions. Another possibility is that dark energy could represent the influence of a new force of nature, one that operates only on the largest scales. While we are familiar with the four known forces, gravity, electromagnetism, and the strong and weak nuclear forces, there may be additional forces that we have yet to detect. These forces could be extremely weak or only become noticeable at vast cosmic distances. If dark energy is driven by such a force, it would challenge our understanding of the universe and lead to a new era of discovery in both physics and cosmology. One of the most striking implications of dark energy is its influence on the ultimate fate of the cosmos. As we've discussed, the accelerated expansion caused by dark energy is leading the universe toward a future in which galaxies move farther and farther apart. Over time, this expansion will make the universe colder, darker, and emptier, as the energy from stars and galaxies is spread thin across an ever-increasing volume of space. In this scenario, known as the heat death, or the Big Freeze, the universe will eventually reach a state of maximum entropy, where no usable energy remains, and all processes cease. However, the specific details of how the universe will evolve depend on the properties of dark energy. If dark energy remains constant, as predicted by the cosmological constant model, the expansion will continue indefinitely, and the universe will slowly drift toward the Big Freeze. On the other hand, if dark energy is dynamic, perhaps a field that evolves over time, different outcomes are possible. One possibility, known as the Big Rip, would occur if dark energy becomes stronger over time, eventually overwhelming all other forces in the universe. In this scenario, the expansion would accelerate to the point where even galaxies, stars, planets, and atoms are torn apart. The idea of the Big Rip is both fascinating and terrifying. It suggests that dark energy could play a role not only in shaping the large-scale structure of the universe but also in determining its ultimate demise. The timing of the Big Rip would depend on the exact nature of dark energy, but if it occurs, it could happen billions or even trillions of years in the future. While this is far beyond the lifespan of the human race or even our planet, it raises profound questions about the future of the cosmos and the role that dark energy will play in its evolution. There are other potential fates for the universe that are less dramatic but equally intriguing. If dark energy weakens over time, the expansion could slow down and eventually reverse, leading to a cosmic contraction known as the Big Crunch. In this scenario, the universe would collapse back into a hot, dense state, possibly setting the stage for a new Big Bang and the birth of a new universe. While this idea has fallen out of favor due to the discovery of the accelerating expansion, it remains a possibility if dark energy behaves in unexpected ways. Another possibility is that the universe will reach a state of equilibrium, in which dark energy and the attractive force of gravity balance each other out. In this case, the universe would expand more slowly over time, eventually reaching a stable state in which galaxies remain at fixed distances from one another. This outcome, known as the Big Bounce, is favored in some cyclical models of the universe, in which the cosmos undergoes repeated cycles of expansion and contraction. In these models, dark energy might play a role in driving the expansion phase of the cycle, while gravity brings the universe back together during the contraction phase. The fate of the universe is not just a question of scientific curiosity. It also touches on some of the deepest philosophical questions about existence and the nature of time. If the universe is destined to expand forever, leading to a cold, dark future, what does that mean for the meaning and purpose of life? Conversely, if the universe undergoes cycles of birth and death, how does that affect our understanding of time and eternity? Dark energy, in its enigmatic role as the driver of cosmic acceleration, forces us to confront these questions and consider the ultimate trajectory of the cosmos. Despite the progress we have made in understanding dark energy, many fundamental questions remain. For example, why did the acceleration of the universe begin only a few billion years ago, long after the Big Bang? What is the true nature of the vacuum, and how does it relate to dark energy? Is dark energy constant, or does it evolve over time? And perhaps most importantly, how does dark energy fit into a unified theory of physics that reconciles quantum mechanics and general relativity? These questions highlight the profound challenge that dark energy presents to both observational and theoretical physics. Solving the mystery of dark energy will likely require not only new observations but also new ideas and approaches that go beyond the current paradigms of physics. As we move into the future, advances in technology and experimental techniques will enable us to probe the universe in greater detail, offering new clues about the nature of dark energy and its role in the cosmos. Ultimately, the search for dark energy is about more than just understanding the fate of the universe. It is about pushing the boundaries of human knowledge and exploring the deepest mysteries of reality. Dark energy represents a frontier of science that could redefine our understanding of the cosmos and our place within it. Whether it leads to the discovery of new forces, new dimensions, or new laws of nature, the pursuit of answers to the dark energy mystery promises to be one of the most exciting and transformative scientific endeavors of the 21st century and beyond. One of the most tantalizing aspects of dark energy is the way it highlights the limitations of our current understanding of the cosmos. Throughout history, science has made leaps forward when confronted with phenomena that couldn't be explained by existing theories. The discovery of dark energy stands as one of the greatest challenges we face in modern physics, and yet, it also represents an extraordinary opportunity for future breakthroughs. At the heart of this mystery lies the nature of the vacuum itself. While we typically think of space as being empty, the concept of vacuum in quantum physics is far more complex. The vacuum is not simply nothing, it is a seething sea of virtual particles that pop in and out of existence, governed by the laws of quantum mechanics. This quantum vacuum plays a crucial role in shaping the fabric of space-time, and might even be the key to understanding dark energy. One idea, known as vacuum energy, suggests that dark energy could be the result of the energy contained in this quantum vacuum. According to this hypothesis, the vacuum has a small but non-zero energy density, which exerts a repulsive force on spacetime, causing the universe to expand. This idea is supported by calculations from quantum field theory, which predict that even the empty space between particles is filled with fluctuating energy. However, there is a major problem with this explanation. The energy predicted by quantum theory is far greater than the amount of dark energy we observe. In fact, the theoretical prediction is off by a staggering 120 orders of magnitude, making it the most significant discrepancy between theory and observation in all of physics. This colossal mismatch, often called the vacuum catastrophe, has led physicists to question whether we are missing something fundamental about the nature of dark energy, or even the nature of space itself. Some have suggested that dark energy might be the result of a delicate balance between different quantum fields, with the observed value of dark energy arising from a fine-tuning of these fields. Others propose that dark energy could be related to new particles or fields that have yet to be discovered. One promising avenue of research is the study of scalar fields, which are fields that can vary in strength over time and space. These fields are different from the familiar vector fields, such as the electromagnetic field, which have both a magnitude and a direction. Scalar fields are simpler in that they have only a magnitude, but they can have profound effects on the structure of the universe. One of the most famous examples of a scalar field is the Higgs field, which is responsible for giving particles their mass. Some physicists believe that dark energy could be associated with a similar type of scalar field, sometimes referred to as quintessence. Unlike the cosmological constant, which is static and unchanging, quintessence would evolve over time, potentially explaining why the universe's expansion began accelerating only a few billion years ago. In this scenario, the strength of the dark energy field could change as the universe ages, leading to different cosmic fates depending on how the field evolves. If the field weakens over time, the expansion could slow down and possibly reverse. If the field strengthens, it could drive the universe toward a more dramatic end, such as the Big Rip. However, finding direct evidence for quintessence or other forms of dynamic dark energy has proven to be extremely difficult. Unlike ordinary matter and energy, dark energy does not emit light, interact with electromagnetic forces, or leave any obvious signatures that can be detected with our current instruments. Instead, its effects can only be observed indirectly, through the motion of galaxies and the large-scale structure of the universe. This makes dark energy an elusive and ghostly presence in the cosmos, one that challenges the limits of our observational technology. In an effort to gain more insight into the nature of dark energy, scientists have turned to advanced techniques such as gravitational lensing, which involves the bending of light by massive objects like galaxies and clusters of galaxies. By studying how light is distorted as it passes through regions of space, astronomers can map the distribution of dark matter and dark energy on large scales. This approach has already provided important clues about how dark energy influences the expansion of the universe, but much more work is needed to fully understand its role. Another promising avenue of research is the study of cosmic microwave background (CMB) radiation, the afterglow of the Big Bang. By analyzing subtle variations in the CMB, scientists can infer the properties of the early universe and how it has evolved over time. These variations also offer valuable information about the effects of dark energy on the universe's expansion. Recent observations from space-based missions such as the Planck satellite have provided some of the most precise measurements of the CMB to date, helping to refine our understanding of dark energy and its role in the cosmos. Additionally, large-scale surveys of galaxies, such as the Sloan Digital Sky Survey and the Dark Energy Survey, are mapping the distribution of galaxies and galaxy clusters across vast stretches of space. These surveys allow astronomers to trace the expansion history of the universe and test different models of dark energy. As these surveys continue to collect data, they will provide an increasingly detailed picture of how dark energy has shaped the universe's evolution. The coming decades promise to bring even more powerful tools to bear on the dark energy problem. New telescopes, such as the upcoming Nancy Grace Roman Space Telescope, formerly known as WFRST, will be specifically designed to study dark energy and its effects on the cosmos. These next-generation observatories will allow astronomers to probe deeper into space and further back in time, providing new insights into the behavior of dark energy over the history of the universe. In addition to observational advances, theoretical physicists are developing new ideas that could shed light on dark energy. Some researchers are exploring the possibility that dark energy might not be a property of space-time itself but rather a consequence of our limited understanding of gravity. This idea is known as modified gravity, and it suggests that Einstein's theory of general relativity may need to be revised or extended to account for the accelerated expansion of the universe. Modified gravity theories come in many different forms, but they all share the common goal of explaining dark energy as a feature of gravity rather than as a separate force or field. Some of these theories involve extra dimensions, as mentioned earlier, while others propose that gravity behaves differently on very large scales than it does on small scales. If one of these theories proves correct, it could lead to a profound revision of our understanding of gravity and the structure of the universe. One intriguing idea within this framework is the notion that dark energy could be an illusion created by our inability to fully comprehend the geometry of spacetime. In this view, the universe might be expanding not because of a mysterious repulsive force but because of the way spacetime is curved on large scales. This curvature could cause galaxies to move apart in a way that mimics the effects of dark energy, without requiring the existence of a new form of energy. While this idea remains speculative, it highlights the possibility that dark energy could be a signal that our understanding of the universe's geometry is incomplete. As physicists continue to explore these possibilities, the mystery of dark energy serves as a reminder of how much we still have to learn about the universe. While we have made tremendous strides in understanding the cosmos over the past century, dark energy stands as one of the greatest puzzles of our time. It challenges our theories, pushes the boundaries of our technology, and forces us to rethink some of the most fundamental assumptions about the nature of reality. Yet, it is precisely this uncertainty that makes the study of dark energy so exciting. The pursuit of knowledge is driven by curiosity and the desire to understand the unknown. Dark energy represents one of the most profound unknowns in modern science, and solving its mystery could lead to revolutionary discoveries that reshape our understanding of the universe. Whether dark energy turns out to be a new force, a property of the vacuum, a modification of gravity, or something even more exotic, its discovery will have far-reaching implications for both science and philosophy. It will affect how we view the cosmos, the laws that govern it, and the future that awaits us. As we continue to explore the mysteries of dark energy, we are reminded that the universe is far stranger and more complex than we ever imagined, and that the quest for knowledge is far from over. The implications of dark energy are not confined to the distant realms of the cosmos. They also touch upon some of the most profound questions about the fate of the universe and, by extension, our place within it. The realization that the universe is expanding at an accelerating rate has radically altered our vision of cosmic evolution and has led to several competing theories about the ultimate destiny of everything that exists. If dark energy continues to dominate the expansion of the universe, one of the most widely accepted scenarios is the so-called Big Freeze. In this model, the universe will continue to expand indefinitely, causing galaxies to move further and further apart from one another. Over billions and trillions of years, this expansion will lead to a cold, dark, and empty universe, where galaxies, stars, and even atoms are spread so thin that they effectively stop interacting with one another. The Big Freeze suggests that the universe will reach a state of maximum entropy, often referred to as heat death, where all energy is evenly distributed, and no meaningful work can be done. In this desolate future, stars will eventually burn out, black holes will evaporate via Hawking radiation, and even the faintest traces of matter will be so dispersed that the universe will become a vast, featureless void. This chilling scenario presents a universe that, in the very distant future, becomes cold and static, devoid of structure and life as we know it. However, the nature of dark energy could also open up other, more dramatic possibilities. For instance, if dark energy's strength increases over time, it could lead to an even more catastrophic outcome known as the Big Rip. In this model, the repulsive force of dark energy becomes so powerful that it overwhelms the gravitational and electromagnetic forces holding galaxies, stars, planets, and even atoms together. As a result, the fabric of space-time itself would be torn apart in a cosmic cataclysm. The Big Rip would begin with the destruction of galaxy clusters, followed by the disintegration of individual galaxies, solar systems, and planets. Eventually, the force of dark energy would rip apart stars, and finally, at the ultimate moment, it would tear atoms and subatomic particles apart. This doomsday scenario predicts that the universe would be completely shredded at a specific point in the future, leading to the end of time itself. Another intriguing possibility is that the influence of dark energy could eventually reverse, leading to a future where the universe stops expanding and begins to contract. This idea is known as the Big Crunch. In this scenario, dark energy might be a temporary phase, and once its influence diminishes, gravity could once again take over, pulling everything back together. Over time, the universe would collapse in on itself, reversing the expansion and culminating in a fiery implosion, possibly returning the universe to a singular state similar to the one that existed before the Big Bang. Some cosmologists have even speculated that the Big Crunch could lead to a cyclical universe, where each cycle of expansion and contraction is followed by a new Big Bang. This idea, known as the Big Bounce, suggests that the universe could be in a never-ending loop of birth, death, and rebirth, with each iteration giving rise to new structures, galaxies, and possibly even new forms of life. In this view, dark energy might play a crucial role in determining when and how the universe transitions between these cycles. While these theories about the future of the universe remain speculative, they highlight the deep connection between dark energy and the ultimate fate of the cosmos. Whether the universe will freeze, rip apart, or collapse in on itself depends on the nature of dark energy, a force we barely understand. As we continue to study dark energy, we are not just probing the mysteries of the universe's expansion, we are also exploring the long-term prospects for existence itself. Beyond these apocalyptic visions, dark energy also raises philosophical questions about the nature of reality. Why does dark energy exist at all? Why does it have the specific properties that cause the universe to accelerate? These questions touch on the anthropic principle, which suggests that certain aspects of the universe's physical laws and constants might be fine-tuned to allow for the existence of life. According to this view, if the value of dark energy were even slightly different, the universe might have evolved in a way that precludes the formation of galaxies, stars, planets, and ultimately, life as we know it. The anthropic principle is controversial among scientists and philosophers because it appears to introduce an element of design or purpose into the laws of physics. Some argue that the apparent fine-tuning of the universe's constants, including dark energy, is evidence that the universe was somehow set up to allow for the existence of observers like us. Others reject this idea, suggesting that the fine-tuning is simply a coincidence, or that there might be other universes with different values of dark energy, where life did not emerge. This idea leads to the concept of the multiverse, the possibility that our universe is just one of many, each with its own set of physical laws and constants. If the multiverse exists, dark energy might vary from one universe to another, and we happen to live in a universe where the value of dark energy is just right to allow for the development of galaxies, stars, and life. While the multiverse remains a speculative idea, it offers a potential explanation for why dark energy has the specific properties that it does. However, the multiverse also presents challenges to our ability to test and observe the nature of dark energy. If other universes exist beyond our observational horizon, we may never be able to directly study them, leaving us with only indirect clues about the nature of dark energy and the cosmos. This limitation raises questions about the scope of scientific inquiry. Can we ever truly understand the fundamental nature of reality? Or are there aspects of the universe that will remain forever beyond our reach? The study of dark energy also forces us to confront the possibility that our current theories of physics might be incomplete. Dark energy seems to defy explanation within the framework of general relativity and quantum mechanics, the two pillars of modern physics. As a result, some physicists believe that understanding dark energy may require a new theory of physics, one that unifies gravity with the other fundamental forces of nature. Such a theory, often referred to as quantum gravity, could provide a deeper understanding of the fabric of space-time and the origins of the universe. One of the most promising candidates for a theory of quantum gravity is string theory, which posits that the fundamental building blocks of the universe are not particles, but tiny vibrating strings of energy. String theory offers the possibility of explaining both gravity and quantum mechanics within a single framework, and it might also provide insights into the nature of dark energy. In some versions of string theory, the properties of dark energy could be related to the geometry of extra dimensions, or to the behavior of higher-dimensional objects known as branes. While string theory is still in its early stages, and many of its predictions remain untested, it represents a bold attempt to solve some of the most profound mysteries in physics, including the mystery of dark energy. If successful, it could revolutionize our understanding of the universe and provide a unified theory that explains everything from the behavior of subatomic particles to the large-scale structure of the cosmos. As we stand at the forefront of this scientific frontier, the mystery of dark energy serves as a reminder of both the power and the limitations of human knowledge. We have made incredible strides in understanding the universe, but dark energy shows us that there is still much we do not know. The discovery of dark energy has opened up a new era in cosmology, one that challenges us to rethink our most fundamental assumptions about the nature of reality and our place in the cosmos. In the end, the quest to understand dark energy is not just a scientific endeavor, it is a journey into the unknown, a search for answers to some of the deepest questions about existence itself. Whether we find those answers in the quantum vacuum, the fabric of spacetime, or the hidden dimensions of the multiverse, the mystery of dark energy will continue to inspire generations of scientists, philosophers, and dreamers to explore the cosmos and unlock the secrets of the universe. The investigation into dark energy has also catalyzed advancements in observational technology, enabling astronomers to peer deeper into the universe than ever before. The tools we use to measure cosmic distances and understand the structure of the universe have evolved dramatically, enhancing our capacity to gather data that could clarify the nature of dark energy. For instance, space-based observatories such as the Hubble Space Telescope and the upcoming James Webb Space Telescope are designed to study the universe in unprecedented detail, helping scientists track the expansion of the cosmos over time. One of the critical methods for understanding dark energy involves analyzing the light emitted by distant supernovae, particularly Type Ia supernovae, which serve as standard candles for measuring astronomical distances. By observing the brightness of these supernovae and comparing it to their redshift, astronomers can infer how far the universe has expanded over specific intervals. This method was instrumental in the discovery of dark energy, revealing that distant supernovae appeared dimmer than expected based on earlier models of a decelerating universe, thus indicating that an unknown force was pushing the universe apart. Additionally, the mapping of the cosmic microwave background (CMB), the afterglow radiation from the Big Bang, has provided insights into the universe's overall structure and composition, including the proportion of dark energy. Projects like the Planck satellite have helped refine our understanding of the CMB, measuring its temperature fluctuations and providing a snapshot of the universe when it was just 380,000 years old. The data collected from these measurements plays a crucial role in our current cosmological models, including the lambda cold dark matter model, which incorporates dark energy as a cosmological constant. Despite these advances, the future of dark energy research remains uncertain. The fundamental questions surrounding its nature, what it is, why it exists, and how it behaves, continue to elude definitive answers. Some researchers have proposed alternative theories to explain the acceleration of the universe, moving away from the idea of a cosmological constant. These include modified gravity theories, such as F.R. gravity, which suggests that gravity may behave differently on cosmological scales than predicted by Einstein's general relativity. In these models, the dynamics of cosmic expansion are altered by changing gravitational forces rather than relying solely on the properties of dark energy. Another area of inquiry focuses on the possibility of dynamical dark energy. This concept posits that dark energy might not be constant but could evolve over time, potentially leading to a universe that transitions between different phases of expansion. If this hypothesis holds, it could explain certain anomalies in cosmological observations that appear inconsistent with a simple cosmological constant model. Dynamical dark energy could also influence the fates of various cosmic structures, such as galaxy clusters and cosmic filaments, leading to a more intricate and nuanced understanding of the universe's evolution. Theoretical physicists and cosmologists also explore the implications of quantum fluctuations on a cosmological scale. According to some theories, vacuum energy could give rise to the effects we attribute to dark energy. Quantum field theories predict that empty space is not truly empty, but teems with virtual particles that momentarily appear and disappear. The energy associated with these fluctuations might contribute to the overall energy density of the universe, potentially resulting in a repulsive force akin to what we observe as dark energy. Understanding the connection between quantum mechanics and cosmology could be key to unraveling the mystery of dark energy. As we continue to confront the enigma of dark energy, collaboration across disciplines becomes increasingly essential. Astrophysics, cosmology, particle physics, and even philosophy converge as researchers seek to create a comprehensive understanding of the universe's behavior. This interdisciplinary approach encourages innovative ideas and theories, pushing the boundaries of human knowledge. Moreover, the implications of dark energy extend beyond cosmological concerns. They resonate with existential inquiries about the nature of reality and our understanding of the universe. The fact that the universe is expanding at an accelerating rate challenges our perceptions of stability and permanence. It forces us to reconsider our place in an ever-changing cosmos, raising profound questions about the fate of life itself. As the universe continues to stretch and evolve, we must grapple with the implications of our existence in a transient reality. Furthermore, the pursuit of knowledge about dark energy has significant philosophical implications. It touches upon ideas of determinism and chaos, highlighting the delicate balance between order and randomness in the cosmos. The universe's accelerating expansion may evoke feelings of insignificance, as it portrays a cosmos indifferent to our struggles and aspirations. Yet, this very indifference is a powerful reminder of the vastness of existence, encouraging us to seek understanding and meaning in a universe that often defies comprehension. The role of humanity in the grand scheme of the universe also comes into focus. As we uncover the mysteries of dark energy, we are not merely passive observers but active participants in a cosmic narrative that spans billions of years. Our quest for knowledge reflects a deep-seated desire to connect with the universe, to understand the forces that shape our reality, and to explore the origins and fate of everything we hold dear. In contemplating the nature of dark energy, we find ourselves at the intersection of science, philosophy, and wonder. The pursuit of answers to these profound questions drives us to explore the unknown, to push the limits of our understanding, and to engage with the cosmic mystery that surrounds us. As we venture forth, we stand on the shoulders of giants, scientists, thinkers, and dreamers who have come before us, continuing a legacy of inquiry that transcends generations. In the grand tapestry of the cosmos, dark energy serves as a thread that weaves together the fabric of our understanding. Each discovery we make brings us closer to unveiling the secrets of the universe, illuminating the path of knowledge while reminding us of the vastness of what remains unexplored. The quest for understanding dark energy is a testament to human curiosity and resilience, a journey that invites us to ask questions, challenge assumptions, and seek the answers that elude us. Ultimately, the mystery of dark energy may not be solved in our lifetimes, and it may even lead to more questions than answers. Yet this uncertainty fuels our desire to explore, to learn, and to connect with the universe around us. It is a reminder that while we may never fully grasp the cosmos's intricacies, our pursuit of knowledge enriches our lives and deepens our appreciation for the beauty and complexity of existence. As we stand on the brink of discovery, looking out into the vast expanse of the universe, we are compelled to confront our own limitations and embrace the unknown. The mystery of dark energy continues to inspire generations of scientists and thinkers, guiding us toward new horizons of understanding. In this cosmic journey, every question we ask and every insight we gain becomes a stepping stone toward a deeper comprehension of the universe, a journey that, ultimately, may define our very humanity. Through the lens of dark energy, we not only explore the universe but also reflect on our place within it. As we seek to understand the forces that govern the cosmos, we engage in a dialogue with the universe itself, one that spans the depths of time and space. In doing so, we reaffirm our commitment to curiosity, exploration, and the unending quest for knowledge that defines our species. Thus, the enigma of dark energy is not merely a scientific puzzle, it is a profound invitation to embark on a journey of discovery. As we seek to uncover the truth behind this mysterious force, we are reminded that the universe is a dynamic, ever-evolving tapestry of wonder and complexity. Each revelation adds another layer to our understanding, illuminating the intricate connections between the cosmos, ourselves, and the fundamental laws that govern existence. The mystery of dark energy encapsulates the essence of humanity's quest for knowledge, a journey filled with challenges, triumphs, and boundless curiosity. As we continue to unravel the secrets of the universe, we are reminded that the pursuit of understanding is a vital part of our existence, a testament to our resilience and determination. Dark energy may remain an enigma for the foreseeable future, but in our search for answers, we find meaning, inspiration, and a deeper connection to the cosmos that surrounds us. As our exploration of dark energy unfolds, we must also consider the broader implications of this mysterious force on the ultimate fate of the universe. Several scenarios emerge, influenced largely by the characteristics of dark energy. Understanding these potential outcomes requires us to delve deeper into the current cosmological models and how they account for dark energy's role in the universe's expansion. One of the prevailing theories about the universe's fate, based on the current understanding of dark energy, is the Big Freeze scenario, also known as the heat death of the universe. In this model, as dark energy continues to drive the accelerated expansion of the universe, galaxies will eventually drift farther apart. Over trillions of years, stars will exhaust their nuclear fuel, leading to a universe that becomes increasingly dark and cold. The cosmic background radiation will continue to diminish, and matter will be left sparse and isolated, creating a vast, empty cosmos. This eventual heat death presents a stark contrast to the vibrant universe we observe today, highlighting the transient nature of existence on a cosmic scale. In contrast, alternative models propose different outcomes. Some theoretical physicists suggest that dark energy might change over time, leading to a different fate for the universe. For instance, if dark energy were to become repulsive at some point, it could result in a scenario where the universe eventually contracts, leading to a Big Crunch. In this scenario, the universe would stop expanding and begin to collapse back into a singularity, similar to the conditions believed to have existed before the Big Bang. While this idea poses intriguing questions about the cyclic nature of the universe, it remains speculative, requiring further investigation into the dynamics of dark energy and its long-term behavior. Another possibility is the Big Rip, a more extreme scenario in which the repulsive effects of dark energy increase over time, ultimately tearing apart galaxies, stars, planets, and even atoms. In this model, as the expansion accelerates, structures in the universe would become increasingly unstable, culminating in a catastrophic end where the very fabric of spacetime is torn apart. The timeline for such an event could stretch across billions of years, but it raises profound questions about the stability of the universe and our understanding of the forces that govern it. These varying outcomes reflect the uncertainty surrounding dark energy and the universe's fate. They underscore the importance of continued research and observation in the field of cosmology. As scientists strive to refine their models and gather more data, they are faced with the challenge of reconciling observations with theoretical predictions. This ongoing dialogue between theory and observation is essential to advancing our understanding of the universe and its ultimate destiny. The search for dark energy's nature is not merely an academic endeavor. It profoundly impacts our understanding of fundamental physics. The quest to uncover what dark energy is ties into broader questions about the nature of gravity, quantum mechanics, and the fundamental forces of the universe. As physicists investigate the properties of dark energy, they seek to bridge the gap between general relativity and quantum mechanics, two pillars of modern physics that, while immensely successful in their respective domains, have yet to be reconciled into a single framework. This reconciliation holds the potential for groundbreaking discoveries that could reshape our understanding of the universe. Many physicists believe that a unified theory of quantum gravity could reveal new insights into dark energy, possibly even linking it to other fundamental phenomena in the universe. As research progresses, the implications of these theories could revolutionize our comprehension of reality itself. As we ponder the implications of dark energy, we are reminded of our place within the cosmos. Humanity's quest for knowledge about dark energy reflects a deep-seated curiosity and an intrinsic drive to understand our universe's mysteries. This pursuit is not merely about answering scientific questions, it connects us to the universe on a fundamental level. The exploration of dark energy invites us to reflect on our existence, the nature of time and space, and the overarching narrative that encompasses all life. The broader philosophical implications of dark energy compel us to consider what it means to be human in a universe governed by forces beyond our comprehension. As we grapple with the concept of an expanding universe driven by dark energy, we confront our limitations and the inevitability of change. The knowledge that the universe is in a constant state of flux prompts us to appreciate the fleeting nature of existence and the beauty inherent in our shared experience. In this context, the story of dark energy becomes a testament to human resilience and ingenuity. Our ability to question, explore, and seek answers is a defining characteristic of our species. This pursuit of knowledge fosters collaboration and dialogue, transcending as we share our discoveries and insights with one another. As we collectively strive to unravel the mysteries of dark energy, we engage in a dialogue that connects us across generations, linking us to those who have come before us and those who will follow. The journey to understand dark energy also highlights the power of curiosity to ignite progress and innovation. As we develop new technologies and methodologies to observe the universe, we simultaneously deepen our appreciation for the interconnectedness of all things. The exploration of dark energy serves as a reminder that the universe is not a collection of isolated phenomena. Rather, it is an intricate web of relationships and interactions that shape the fabric of reality. Furthermore, as we engage with the mysteries of dark energy, we must remain mindful of the ethical considerations surrounding scientific inquiry. The pursuit of knowledge comes with responsibilities, particularly as we explore the fundamental workings of the universe. Scientists must navigate the implications of their discoveries and ensure that their research serves the greater good, contributing to a more profound understanding of our place in the cosmos. The exploration of dark energy is not merely a scientific challenge, it is an invitation to consider our role within the universe. As we seek answers to the questions that dark energy poses, we also confront our responsibilities as stewards of knowledge and custodians of the Earth. This awareness encourages us to think critically about our actions and their impact on the world, fostering a sense of responsibility that extends beyond scientific inquiry. As the investigation into dark energy continues, we are reminded that the quest for understanding is an integral part of the human experience. The challenges we face in unraveling the mystery of dark energy reflect the complexity of existence itself, a tapestry woven from questions, discoveries, and insights that shape our understanding of reality. Ultimately, the journey to comprehend dark energy encapsulates the spirit of exploration that defines humanity. Our quest to understand the forces that shape the universe is a testament to our curiosity and determination. As we navigate the mysteries of dark energy, we are propelled forward by the realization that every question we ask, every discovery we make, adds to the richness of our understanding and deepens our connection to the cosmos. The allure of dark energy, with its profound implications and enigmatic nature, invites us to embrace the unknown and venture into uncharted territory. In doing so, we honor the legacy of those who have come before us, forging a path toward enlightenment that will guide future generations in their pursuit of knowledge. As we continue our exploration of dark energy, we stand at the threshold of discovery, ready to uncover the secrets that lie beyond the veil of the known. The mystery of dark energy encapsulates humanity's quest for knowledge, inviting us to explore the cosmos and confront the profound questions that shape our existence. As we unravel the complexities of dark energy, we engage in a journey that transcends the boundaries of science, philosophy, and spirituality, reminding us of the beauty and wonder inherent in our shared experience of the universe. With every discovery, we move closer to understanding the fundamental forces that govern the cosmos, illuminating the path of knowledge that connects us all. The exploration of dark energy serves as a testament to our resilience, curiosity, and determination, a reminder that even in the face of uncertainty, the quest for understanding is a vital part of what it means to be human. Through the lens of dark energy, we see the universe as a dynamic, ever-evolving tapestry, rich with complexity and wonder. As we continue to push the boundaries of our understanding, we remain committed to exploring the mysteries of the cosmos, driven by an insatiable curiosity that inspires us to seek answers and embrace the unknown. In this pursuit, we honor the legacy of those who have come before us, celebrating the spirit of exploration that defines our species. The journey to understand dark energy is an integral part of our shared narrative, a story that continues to unfold, inviting us to participate in the cosmic dance that shapes our existence. As we gaze into the vastness of the universe, we are reminded of the profound mysteries that lie ahead, waiting to be uncovered. The enigma of dark energy beckons us forward, inviting us to explore, discover, and ultimately connect with the cosmos in ways that transcend our understanding. In doing so, we reaffirm our commitment to curiosity and knowledge, embarking on a journey that promises to reshape our understanding of the universe and our place within it. As we delve deeper into the nuances of dark energy, it's essential to explore the various lines of evidence that support its existence, and the role it plays in the universe's expansion. The narrative surrounding dark energy is woven from multiple strands of observational data, theoretical considerations, and experimental confirmations, creating a comprehensive picture that challenges our understanding of physics and cosmology. One of the most significant pieces of evidence for dark energy emerged from the study of supernovae, specifically Type Ia supernovae. In the late 1990s, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, conducted observations of these stellar explosions to measure the expansion rate of the universe. Type Ia supernovae are considered standard candles because their intrinsic brightness is well understood, allowing astronomers to determine their distance based on their observed brightness. The groundbreaking findings revealed that the universe's expansion is not slowing down, as previously thought, but accelerating. This revelation was both surprising and counterintuitive, leading to the introduction of the term, dark energy, to describe the unknown force driving this acceleration. The implications of this discovery were profound, reshaping our understanding of cosmology and prompting scientists to seek a deeper understanding of the nature of dark energy. In addition to supernova observations, other lines of evidence bolster the case for dark energy. Measurements of the cosmic microwave background radiation, which is the remnant heat from the Big Bang, provide critical insights into the universe's overall structure and composition. Data from missions like NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite have mapped temperature fluctuations in the cosmic microwave background, offering clues about the universe's expansion history. These measurements reveal that approximately 68% of the universe is composed of dark energy, with about 27% attributed to dark matter and only around 5% consisting of ordinary matter, including stars, planets, and galaxies. This staggering imbalance underscores the dominance of dark energy in shaping the universe's evolution, yet its nature remains elusive. Another compelling line of evidence comes from observations of large-scale structures in the universe. The distribution of galaxies and galaxy clusters offers insights into the interplay between dark energy, dark matter, and ordinary matter. Gravitational lensing, an effect predicted by Einstein's theory of general relativity, occurs when massive objects like galaxies bend light from more distant objects. This phenomenon provides a way to map the distribution of both visible and invisible matter in the universe. When astronomers analyze gravitational lensing patterns, they find that the effects of dark energy influence the formation and evolution of cosmic structures. These observations suggest that dark energy is not only a driving force behind the accelerated expansion but also plays a significant role in shaping the universe's large-scale structure. Moreover, the interplay between dark energy and dark matter is a subject of ongoing research. While dark matter is thought to clump together under the influence of gravity, creating galaxies and galaxy clusters, dark energy acts as a counterbalance, driving the universe's expansion. Understanding how these two components interact is crucial for developing a comprehensive model of the universe's evolution. As scientists continue to investigate the nature of dark energy, they have proposed various theories to explain its origin and behavior. One prominent theory is the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. The cosmological constant represents a constant energy density that fills space homogeneously, exerting a repulsive gravitational effect. While this concept provides a straightforward explanation for dark energy, it raises questions about its value and why it is so small compared to the energy scales of fundamental physics. Another avenue of exploration involves modifications to general relativity itself. Some theories propose that dark energy is a manifestation of new physics beyond Einstein's framework, leading to alternative gravity theories. For instance, gravity modifies the equations of general relativity by allowing the gravitational force to vary with the curvature of spacetime. These modifications aim to reconcile the observed acceleration with a more fundamental understanding of gravity, but they face challenges in matching observations across various scales. Additionally, there are theories suggesting that dark energy could be linked to quantum mechanics. Quantum field theory posits the existence of vacuum energy, where fluctuations in empty space produce energy contributions. However, the calculated vacuum energy density from quantum field theory vastly exceeds the observed value of dark energy, leading to what is known as the vacuum catastrophe. This discrepancy highlights the need for a deeper understanding of the fundamental principles governing both quantum mechanics and cosmology. The exploration of dark energy also intersects with the quest for a unified theory of physics. Many physicists believe that a comprehensive understanding of dark energy could provide crucial insights into the elusive theory of everything that would unify general relativity and quantum mechanics. By investigating the nature of dark energy, scientists may uncover new principles that could reshape our understanding of the universe at its most fundamental level. In addition to theoretical considerations, experimental efforts continue to probe dark energy's properties. Upcoming missions, such as the European Space Agency's Euclid satellite and NASA's Wide Field Infrared Survey Telescope, WFIRST, aim to map the geometry of the universe and investigate the distribution of dark energy. These projects will gather extensive data to help refine our models and shed light on the nature of dark energy, potentially leading to groundbreaking discoveries. As we contemplate the implications of dark energy, we are also prompted to consider the broader philosophical questions it raises. The existence of dark energy challenges our understanding of reality and compels us to reflect on the nature of existence itself. If the universe is governed by forces we cannot directly observe or fully comprehend, what does that mean for our understanding of the cosmos and our place within it? This inquiry into dark energy invites us to embrace humility in the face of the universe's vastness. It underscores the importance of questioning our assumptions and remaining open to new possibilities. The pursuit of knowledge is a continuous journey, one that requires us to confront the limits of our understanding while remaining committed to the exploration of the unknown. As we strive to unravel the mysteries of dark energy, we find ourselves standing at the intersection of science and philosophy. The quest to comprehend dark energy serves as a reminder of the interconnectedness of all knowledge, how scientific inquiry can inspire philosophical reflection and vice versa. This interplay enriches our understanding of the universe and invites us to engage in a dialogue that transcends disciplinary boundaries. Ultimately, the mystery of dark energy invites us to participate in a grand narrative that encompasses the evolution of the cosmos. It challenges us to confront our limitations while inspiring us to seek answers and expand our horizons. The ongoing exploration of dark energy promises to deepen our understanding of the universe and reveal the fundamental truths that govern our existence. As we continue to navigate this uncharted territory, we recognize that our pursuit of knowledge is not merely an intellectual endeavor but a deeply human endeavor. It connects us to each other and the universe, reminding us of the beauty and complexity of existence. Through the lens of dark energy, we glimpse the grandeur of the cosmos and our role in its unfolding story. The mystery of dark energy is a captivating and complex enigma that challenges our understanding of the universe. Through the study of dark energy, we confront profound questions about the nature of reality, the forces that shape our cosmos, and our place within it. As we continue our exploration of dark energy, we are reminded of the power of curiosity and the importance of embracing the unknown. This pursuit not only deepens our understanding of the universe but also connects us to the shared human experience of seeking knowledge and understanding. In this journey, we find not only answers but also the inspiration to keep questioning, exploring, and marveling at the wonders of the cosmos that lie ahead. Continuing our exploration of dark energy, we encounter yet another layer of complexity: the role of observational cosmology in understanding this enigmatic force. The study of dark energy is not merely a theoretical endeavor, it is deeply rooted in empirical observation and cutting-edge technology. As we look to the future, the advancements in observational techniques promise to shed more light on this cosmic mystery. One of the key tools in observational cosmology is the use of large-scale galaxy surveys. These surveys map the distribution of galaxies across vast distances, providing crucial information about the structure of the universe. Projects like the Sloan Digital Sky Survey (SDSS) and the Dark Energy Survey (DS) have been instrumental in gathering data that inform our understanding of dark energy. By analyzing how galaxies cluster and how their distribution changes over time, astronomers can infer the influence of dark energy on cosmic evolution. The growth of cosmic structures, such as galaxy clusters, is also linked to dark energy. As the universe expands, the rate at which structures form and evolve is affected by the interplay between gravity and the repulsive force of dark energy. By studying the evolution of these structures over time, researchers can better understand how dark energy influences the growth and behavior of galaxies and galaxy clusters. Another innovative method involves gravitational wave astronomy. Gravitational waves, ripples in space-time caused by massive accelerating objects, were first detected by LIGO in 2015. These events provide a new way to measure distances in the universe, offering a complementary approach to traditional cosmological methods. By analyzing the properties of gravitational waves from events such as neutron-star mergers, scientists can obtain additional insights into the expansion of the universe and the role of dark energy. One of the most exciting prospects in the field of dark energy research is the potential for discoveries that could radically alter our understanding of physics. The phenomenon of cosmic acceleration suggests that the universe is not merely expanding but is also undergoing an accelerating transformation. This realization raises profound questions about the future of the universe and its ultimate fate. One possibility is that dark energy continues to dominate the universe, leading to a scenario known as the Big Freeze. In this scenario, galaxies move away from each other at an accelerating rate, leading to a universe that becomes increasingly cold and dark over trillions of years. As stars burn out and galaxies drift apart, the cosmos may approach a state of near absolute zero temperature, where no significant events occur. Alternatively, some theories propose the possibility of a Big Rip, in which the force of dark energy increases over time, eventually tearing apart galaxies, stars, planets, and even atomic structures. In this extreme scenario, the very fabric of space-time could be disrupted, leading to a catastrophic end to the universe as we know it. Such a fate raises philosophical questions about the impermanence of existence and the nature of cosmic life cycles. Conversely, some researchers explore the possibility of a cyclic universe, where the expansion and contraction of the universe lead to repeated cycles of creation and destruction. In this model, dark energy might play a pivotal role in each cycle, influencing the dynamics of the universe's evolution. Such theories challenge our understanding of time, causality, and the fundamental nature of existence. The ongoing quest to understand dark energy also prompts questions about the fundamental forces of nature. The relationship between dark energy and the other fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, remains a topic of intense study. Some researchers investigate whether dark energy could be connected to other physical phenomena, such as quantum entanglement, or the behavior of particles at the quantum level. These explorations may lead to a deeper understanding of the universe's fundamental structure and the nature of reality itself. As we contemplate the implications of dark energy, we are also reminded of the historical context of cosmological inquiry. The journey to uncover the mysteries of the universe has spanned centuries, from ancient astronomers gazing at the night sky to contemporary physicists conducting experiments in particle accelerators. Each advancement has expanded our understanding of the cosmos, revealing the complexities and wonders that lie beyond our immediate perception. This historical perspective serves as a reminder of the enduring nature of human curiosity and the relentless pursuit of knowledge. The exploration of dark energy reflects our innate desire to understand the universe and our place within it, echoing the sentiments of early philosophers and astronomers who gazed at the stars in awe. In this regard, the study of dark energy is not just a scientific endeavor, it is a testament to the human spirit's quest for understanding. Furthermore, the implications of dark energy extend beyond theoretical physics. They touch upon philosophical and existential questions that have intrigued humanity for millennia. The nature of existence, the fate of the cosmos, and our role within the grand tapestry of the universe are questions that resonate. As we grapple with the mystery of dark energy, we are compelled to confront the fundamental nature of reality and our place in the cosmic narrative. This philosophical inquiry invites us to reflect on the significance of our existence. The vastness of the universe, coupled with the enigmatic nature of dark energy, underscores the delicate balance between knowledge and ignorance. While we have made tremendous strides in our understanding, there remain profound mysteries that challenge our comprehension and inspire awe. As scientists continue to explore dark energy, we are reminded of the importance of collaboration and interdisciplinary approaches in the pursuit of knowledge. The intersection of physics, astronomy, philosophy, and even art allows for a richer exploration of the cosmos and a deeper appreciation for its mysteries. The study of dark energy exemplifies the collaborative nature of scientific inquiry, where diverse perspectives and expertise converge to illuminate the unknown. In this pursuit, education and public engagement play a vital role. As our understanding of dark energy evolves, it becomes increasingly important to share these discoveries with the broader community. Engaging the public in discussions about dark energy fosters curiosity and inspires the next generation of scientists, philosophers, and thinkers. By demystifying complex concepts and making them accessible, we empower individuals to participate in the ongoing exploration of the universe. Ultimately, the mystery of dark energy is a captivating journey that invites us to ponder the nature of existence, the forces that shape our universe, and the profound questions that lie at the heart of human inquiry. As we continue to unravel the complexities of dark energy, we find ourselves engaged in a narrative that transcends disciplinary boundaries, inspiring collaboration, curiosity, and a deeper appreciation for the wonders of the cosmos. The exploration of dark energy is not merely a scientific pursuit, it is a profound inquiry into the nature of reality and existence. As we strive to understand the forces that drive the universe's expansion, we are reminded of the interconnectedness of all knowledge and the importance of embracing the unknown. The journey to comprehend dark energy is a testament to human curiosity, resilience, and the enduring spirit of exploration. As we venture forth into the cosmos, we carry with us the hope of discovery, the joy of inquiry, and the promise of new understanding that lies ahead. Through our collective efforts, we continue to illuminate the mysteries of dark energy and unveil the secrets of the universe, revealing the beauty and complexity of the cosmos that surrounds us. Continuing our exploration of dark energy, we must also address the ongoing debates and challenges faced by the scientific community in their efforts to decode this enigmatic force. As researchers delve deeper into the nature of dark energy, They confront a series of significant questions that test the boundaries of current knowledge and understanding. One major issue in the study of dark energy is the discrepancy between different observational data sets. For example, measurements of the universe's expansion rate, known as the Hubble constant, have shown a troubling inconsistency. Two independent methods, the cosmic microwave background (CMB) measurements from the Planck satellite and local distance measurements using supernovae, have produced conflicting results regarding the expansion rate of the universe. This inconsistency raises questions about our understanding of dark energy and its role in cosmic evolution. Resolving this tension is crucial because it could suggest that our current models of dark energy, including the cosmological constant and quintessence, may need significant revision. Researchers are now exploring alternative theories that could account for this discrepancy. Some propose that modifications to general relativity at cosmological scales could provide a better fit to the observational data. Others consider the possibility that our understanding of the early universe may be incomplete, requiring new physics to bridge the gap between observations and theoretical predictions. The challenges posed by dark energy extend beyond observational discrepancies. The very nature of dark energy itself remains one of the most profound mysteries in modern cosmology. Various theories have been proposed to explain dark energy, each with its implications for our understanding of the universe. One prominent theory is the cosmological constant, which was first introduced by Albert Einstein in 1917. This constant represents a uniform energy density that fills space homogeneously, acting as a repulsive force that drives the accelerated expansion of the universe. While the cosmological constant is a simple and elegant solution, it faces challenges known as the fine-tuning problem. The observed value of dark energy is incredibly small compared to theoretical predictions from quantum field theories, leading to questions about why the cosmological constant is so finely tuned to yield the current expansion rate of the universe. In response to these challenges, alternative models have emerged. One such model is quintessence, which posits that dark energy is dynamic rather than constant. Quintessence involves a scalar field that evolves over time, potentially leading to varying effects on cosmic expansion. This model allows for a more flexible approach to understanding dark energy, but it also introduces complexities regarding the nature and behavior of the scalar field. Another intriguing avenue of exploration involves the concept of modified gravity. In this framework, researchers investigate whether deviations from general relativity at large scales could account for the observed acceleration of the universe. Theories such as F.R. gravity and DGP, Dvali-Gabadad's model are examples of modified gravity approaches that aim to reconcile observations with fundamental physics. These theories not only challenge our understanding of dark energy but also prompt re-evaluations of gravity itself. As we ponder the implications of these theories, it is essential to recognize that the pursuit of understanding dark energy is intertwined with the broader quest for a unified theory of physics. The interplay between dark energy, gravity, and other fundamental forces raises profound questions about the nature of reality and the fundamental principles governing the cosmos. Researchers are working tirelessly to connect the dots, seeking to construct a cohesive framework that encompasses both the microscopic world of quantum mechanics and the macroscopic universe of cosmology. In this context, advancements in technology and instrumentation play a crucial role in shaping the future of dark energy research. The next generation of telescopes and observatories promises to enhance our observational capabilities, allowing for more precise measurements and deeper insights into the nature of dark energy. Projects like the James Webb Space Telescope, JWST, the Vera-C, Rubin Observatory, and the European Space Agency's Euclid mission are poised to revolutionize our understanding of the universe. The JWST, launched in December 2021, is designed to explore the distant universe, unveiling the formation of galaxies, stars, and planetary systems. By studying the light from some of the earliest galaxies, JWST will provide valuable data on cosmic evolution and the role of dark energy in shaping the universe's structure. Its infrared capabilities will enable scientists to observe phenomena previously obscured by cosmic dust, offering a new perspective on the cosmos. The Vera C. Rubin Observatory, set to become operational in the coming years, will conduct the Legacy Survey of Space and Time, LSST. This ambitious project aims to map the entire visible sky, capturing images of billions of galaxies and providing insights into their distribution, clustering, and evolution. By monitoring the brightness of supernovae and other transient events, the LSST will contribute to our understanding of cosmic expansion and the influence of dark energy. The Euclid mission, slated for launch by the European Space Agency, focuses specifically on mapping the geometry of the dark universe. By combining measurements of galaxy shapes, clustering, and gravitational lensing, Euclid aims to provide critical insights into the nature of dark energy and its effects on cosmic structure. This mission will also complement the findings from other observational programs, offering a comprehensive view of the universe's evolution. As these technological advancements unfold, the collaboration between theoretical physicists, observational astronomers, and engineers will be vital. The synthesis of ideas and expertise from diverse fields is essential for addressing the challenges posed by dark energy. It is through this collaborative spirit that we may unlock the secrets of the universe and deepen our understanding of the forces that govern cosmic evolution. In contemplating the implications of dark energy, we are reminded of the profound interconnectedness of all things. The forces that shape the universe extend beyond the realm of physics. They touch upon the human experience, our understanding of time and space, and our search for meaning. The study of dark energy invites us to reflect on the fragility of existence, the fleeting nature of time, and the beauty of the cosmos that surrounds us. In essence, the mystery of dark energy serves as a reminder of our collective journey through the cosmos. It is a testament to the enduring human spirit of inquiry, the quest for understanding, and the capacity to embrace the unknown. As we navigate the complexities of dark energy, we participate in a narrative that transcends disciplinary boundaries, uniting science, philosophy, and art in a shared exploration of the universe's mysteries. This ongoing journey invites us to celebrate the wonders of the cosmos while acknowledging the uncertainties that accompany our quest for knowledge. As we venture into the future of dark energy research, we do so with a sense of humility, recognizing that our understanding is continually evolving. Each discovery brings us closer to unraveling the intricate tapestry of the universe, revealing new layers of complexity and beauty. The exploration of dark energy represents one of the most exciting frontiers in modern cosmology. It challenges our understanding of the universe, provokes profound philosophical questions, and invites us to reflect on our place within the cosmic narrative. As scientists, philosophers, and curious minds engage in this ongoing inquiry, we are reminded of the power of collaboration, the importance of embracing the unknown, and the beauty of the universe that inspires us all. Through our collective efforts, we strive to illuminate the mysteries of dark energy, unveiling the secrets of the cosmos and enriching our understanding of existence. As we look to the stars, we carry with us the hope of discovery, the joy of inquiry, and the promise of new understanding that lies ahead. The mystery of dark energy is not just a scientific puzzle, it is a reflection of the human experience, a journey into the heart of the universe, where the answers to our deepest questions may one day be revealed. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.